Today we cover another new integration technique, trig substitutions. So a trig substitution can be used to simplify integrals that involve an expression that has a constant squared plus or minus the variable squared. So for example, I want to find the integral of 1 over radical 9 minus x squared dx. So we're going to perform a strange substitution to make this integral tractable. Where the substitution comes from, we'll talk about when we're done, but I'm just going to tell you we're going to substitute x equals 3 sine theta. I'm going to let x equal 3 sine theta, which means I'm going to make my integral have thetas in it instead of x's, which means I also need to replace the dx. So I'm going to calculate dx d theta, the derivative of what I let x be, which is going to be 3 cosine theta, and then solve for the dx because I want to replace the dx. So dx is going to be 3 cosine theta d theta. So now I go back to my integral, and I'm going to replace all of the x's I see with 3 sine thetas. So I have the square root of 9 minus 3 sine theta squared. So I replace the x with 3 sine theta, and then times dx, which I'm replacing with 3 cosine theta d theta. All right, so now I have some algebra work to do. This becomes the integral of 1 over the square root of 9 minus. Now when I square 3 sine theta, you have to square the 3 and you get 9, and the sine to get sine squared theta, times 3 cosine theta d theta. Okay, now under that radical, I have two terms, both of which have a 9 in them. So I'm going to factor out a 9. So I have the integral of 1 over the square root of 9 times 1 minus sine squared theta times 3 cosine theta d theta. Now there's a trig identity that involves 1 and sine squared. So I'll do a little aside over here to remind you. Sine squared theta plus cosine squared theta always equals 1. That's the Pythagorean trig identity. If I subtract sine squared from both sides of this equation, I get cosine squared theta equals 1 minus sine squared theta. So 1 minus sine squared can be replaced with cosine squared. So that's what I'm going to do in my next line. I have the integral of 1 over square root of 9 cosine squared theta. Replacing 1 minus sine squared with cosine squared, and then I have times 3 cosine theta d theta. Now I can take the square root of the denominator, because now this is 9 times cosine squared. Okay, so this is going to be the integral of 1 over 3 cosine theta. Square root of 9 is 3. The square root of cosine squared is cosine, times 3 cosine theta d theta. And then my 3 cosine thetas cancel. One on the top, one on the bottom. So this is just the integral of 1 d theta, which is theta plus c. Now though, my original problem had x's in it, not thetas, so I have to translate back to x's. So I have to go back to my original substitution equation. X equals 3 sine theta. I'm going to write this down here. X equals 3 sine theta. So I just need to solve for theta so that I can replace this theta with an expression involving x. So I have sine theta equals x over 3. Just divide both sides by 3. And then take the inverse sine of both sides. So theta is equal to the arc sine, or the inverse sine, of x over 3. And that's what I plug in for theta. Arc sine of x over 3 plus c. Okay, so that worked because I had some really nice cancellations. So choosing my x equals 3 sine theta, choosing that substitution was done strategically so that it would get rid of the square root in the radical, because I would have the square root of a perfect square and they would cancel. So the general rule for choosing your trig substitution comes from the first page of your packet. If you have an integral that has an a squared minus x squared alone or under a radical, make your substitution be x equals a sine theta, and then this identity will come in handy, the Pythagorean identity for sine squared and cosine squared. If your integral has a squared plus x squared alone or under a radical, use the substitution x equals a tan theta, and then use this alternate version of the Pythagorean identity. Tangent squared plus 1 equals secant squared.